Hello and welcome. So we've almost made it through our first week of our sort of reinvented class. But let's start by just doing our usual announcements. So the things you got to keep in mind for the next little while are that our next homework will be due on Sunday. That's for the last material that will be on the exam. So ideally, I would recommend finishing that as early as you can, so you have more time to study, the exam as a whole. Yeah, and that brings me to the exam. So our exam 2 will be on Monday, March 30th. It's going to cover sections 2.6 through 3.6. And then on Monday, the way the exam is going to work is we're not going to have any Zoom session like that, like we're doing right now. I'm just going to give you the entire time to do the exam. And I will send out an email that contains a PDF of the exam at, let's see, 2 p.m. So the exam goes out to you guys at 2 p.m. and it will be due in OneNote at 4 p.m. Okay, so I'll give you 2 hours to do the exam, and you turn it in the same way you did your quizzes. So you can either print it out and write on the exam, or you can use separate pieces of paper and write out your answers. Just keep in mind, if you're writing it on a separate piece of paper, please make sure it's clear like which work goes with which problem. And yeah, turn it in on OneNote. And when you're putting things in OneNote, make sure like the entire, like all the sheets show up. So you should be able to read the writing when you insert that. It shouldn't just have a little file icon, because the way we're going to grade them is we're actually going to just write on those pictures in OneNote so that you can see them as well as we can see them. And so yeah, the exam will be 2 hours long and due in OneNote. And yeah, so if you do have a question during the exam, I'm going to set up a chat room that I'll send out with the exam that you can come ask a question. Though other than that, please don't use any internet. I'm going to try to hold you guys to the honor code. So yeah, so that's Monday. Do you guys have any questions about the exam?
How many questions would be in the exam?
I think there's 10 or 11. I don't quite remember. It's about the same length as the first exam. So it's only intended to take you, less than 75 minutes. I'm just giving you the extra time for sort of logistical reasons, like, scanning, uploading, writing everything out, receiving and sending emails, that sort of thing. So the format will be very similar to the first exam, with the exception that I kind of eliminated some of the multiple choice. So there still will be 2 multiple choice questions. One will ask you to show your work, though, so you can still get partial credit on that one. And so there's only one like true multiple choice question left on it. Okay. Any other questions? And yeah, Jesper, I did get everybody's quiz. Some people's I had to fix manually to get it to show up. Okay. So the way today is going to work is we're going to do some review problems, and I'm going to give you the review problems, then I'm going to give you a little time to work on them, and then we'll go through them together. So here's our first problem. I'd like you to take some time. I'll give you, say, 5 or 6 minutes. Pretend this is an exam question and see how far you could get. Okay, and if you have questions, feel free to either ask them in chat or verbally. We do have a TA here who can help answer any questions if you get stuck or something. And then we'll come back and go through it together. So yeah, take 5 minutes, give it a try. Okay, so let's go ahead and go through this together now. So we're asked to make a linear approximation to estimate this. And so the important thing, so there's kind of a couple things to remember about linear approximation, right? So the first thing is that, whenever you take a linearization, we have this important formula, which is basically just the equation of the tangent line, right? And so we want to use a formula like this somehow. And so what we have to identify are what function are we using and what's the c value, okay? And we want it so that when we take so I guess the easiest thing to identify is, so we're trying to identify what cosine of 91 degrees is, or estimate that. And 91 degrees is like a sort of not a nice angle. Like, we don't know how to compute with it very well. So what we're going to do instead is we're going to use an angle that's nearby 90 degrees. So C is usually your nice value. So you take your nice value C, which here we're going to use to be the nice value of 90 degrees. But we're going to use radians and not degrees. And so there's an important reason why you should use radians and not degrees. And the reason is, whenever you're doing a problem that involves calculus and you're taking derivatives of sine and cosine functions, it turns out that if you use degrees, the formulas are different. The formulas for the derivatives are different. They'll be off by a factor of pi over 180. So the formulas we learned are only true in radians. Okay, and so to avoid that, it's easier if we just convert everything to radians. Okay, so we're going to use C as pi over 2. And the function we're going to use is cotangent of x, because ultimately we want to know what f of 91 degrees is. So we throw this into our formula. And in order to do that, we have to calculate some things. So we need f of c. So that would be cotangent of pi over 2. Which is cosine over sine. If you work this out, cosine is 0 at pi over 2, and sine is 1. So overall, this is 0. Then we need the derivative. So let's just find the derivative in general. That'll be minus cosecant squared. If we plug in our c value, that'll be minus cosecant squared of pi over 2, which is, cosecant's 1 over sine. So this is like minus 1 over sine squared of pi over 2. Sine of pi over 2 is 1, so this just all works out to be minus 1. Okay, so if we put that in our formula, then our linearization at c is, our linearization at the nice value c is, so it's the derivative times x minus our c value plus f of our c value, which was just 0. So if we just simplify this a little, it's this kind of nice simple function, minus x plus pi over 2. Okay. And then remember, the central idea behind linearization is, it's like if you have a function and you take the linearization, you're taking the tangent line, and then the idea is if you stay close by, the difference between these is small, right? So here, the black thing is f of x, the line is L of x, and so kind of the mathematical way of writing that is that the thing we want to know or estimate is cotangent of 91 degrees. That's f of 91 degrees. But let's write that in terms of radians. So that would be f of 91 times pi over 180. because that's the conversion ratio between degrees and radians. And so if we don't know what this is exactly, we can approximate it by instead plugging it into our simple formula, which is the line. So this is the estimating part, is that the function is approximately equal to the value of the tangent line on the tangent line, which we can figure out a little bit more easy. And so L of this thing is minus that. So I'm plugging it into here. Plus pi over 2. So this is really just the answer. If we want to simplify it a little bit, which you don't have to do on like an exam, but we can make this look a lot nicer by recognizing that pi over 2 is really just 90 pi over 180. And so 90 minus 91 will just be minus. Okay. So that would be our answer. And that's in radians. Well, actually, no, this is just a number. It's an output. It doesn't have any sort of units. Okay, so questions about that one? Yeah, Elizabeth?
So you'll accept either answer on the exam.
Correct, yes. Yeah, you don't need to simplify unless unless I specifically ask you to. Anybody else? So again, like the idea behind linearization is you have a function where you have sort of an awkward thing that you don't quite know how to compute directly. So what you can do is instead choose a nice value nearby, take the linearization at the nice value, and then plug in the actual value you want. Those are essentially the idea. Okay, so let's move on to another problem. Would you guys like to see another graphing one? You could just say yes or no in chat. We did a lot yesterday. Well, we did 2 yesterday, but I kind of expect it's one of the more difficult things, so.
I have a question.
Yeah.
I remember when we did it in the class, one time we talked about overestimate and underestimate.
Uh-huh.
Is this with linearization, and how do we do that? Are we going to be asked to determine that in the exam?
Yeah, it is sort of fair game for the exam.
So how do we do it? Because I just forgot.
So whenever you're looking at whether something's an overestimate or an underestimate, you kind of have to understand what the graph looks like. So I can't ask you something where you don't know what the graph looks like. So for cotangent, for example, let's see. Cotangent must look like something like this. Whoops, let's try that again. So cotangent is sort of like a shifted upside down version of tangent. So it repeats infinitely often, or it repeats an infinite number of times. And if you look at the graph, this here is pi over 2. Okay, so if you were to zoom in on this, we were asked to find, so the red part is cotangent of x. And we were asked to find something a little bit larger than pi over 2, right? So that would be, but what we did is we took the linearization at pi over 2. So if I drew out the tangent line there, right, then you'll see that if you go to 91 degrees, which is maybe over here somewhere, right? Which one's on top, the line or the function? The green line's on top, right? So that means our linearization, which was the thing we took, So the green thing was the L. Maybe the colors are getting confusing here, but so L of x was the bigger one. So our thing was an overestimate. The actual answer should be a little bit more negative. So it really just matters which one's on top. Is it the line or the function? That's how you tell. Does that answer your question?
Yes, so like the Lx is like 490, and then the red one is like for the equation.
So the red function is cotangent of x, and the green line is the linearization. And we were plugging, so this is 90 degrees. This is 91 degrees. And so at 91 degrees, our estimate, which is from the line, was bigger than the one that was actually on the function.
So for example, if we had to find the linearization for like 60, or actually not 60, but like less than 91, which is probably 89, then we will be not overestimate, below estimate. Since
Yes, that's correct. Yeah, if I had asked you to estimate at like 89 degrees, then yeah, you'd have like a 89. Oops, that's huge. Yeah, you'd have like an 89 here, and the line would be smaller than the function. So it would be
to determine overestimate or like less than estimate or below estimate.
Yeah, so I don't really care how you rewrite it. You could just say the value is too small, but yeah, ours was an overestimate. If you did it the other way, it would be an underestimate.
Okay, got it. Thank you.
Okay, so let's move on to this problem. So that did sound like people want to do some more graphing. That's fair enough. So maybe take another, maybe a little more than 5 minutes because this is a long problem. So, but just take some time and give this one a try, and then we'll come talk about it. Okay. So you probably didn't get all the way through this, but let's go ahead and start going through it together, just for the sake of time. So maybe we can hit a couple more questions. So part A asks us to find the asymptotes. And we know that there's 3 types here. And what we can recognize is that there should be at least one horizontal, because the degree of the numerator and the degree of the denominator are the same. So I would expect there to be one of this, because it's rational. I would expect there to be one vertical, because the denominator can be 0. And I would expect there to be no slants. But if you can't immediately look at it, let's just go through the process. So for part A, for asymptotes, let's just pick one to start with. It doesn't really matter what order you do it in. Let's say we start with horizontal. So remember, the horizontal limits, horizontal asymptotes come from taking the limits at infinity. It's asking what happens as you go really far to the right. Does it approach a line or not? And so let's see, our function was this. And so you could take the long route here and identify that the largest power of x here is x squared, and multiply top and bottom by 1 over x squared. And that'll work. And yeah, so on the bottom does have highest power of x squared, because this x inside the squared, you always have to combine the 2 powers if it's inside something. But a quicker way to do it would be to recognize that the degree of the numerator and the degree of the denominator are the same. And so we would take the ratio of the coefficients of the leading terms. The only thing you would have to be careful of is that really, because this 1 is inside of a square on the bottom, it would come out as a 1 squared, which doesn't matter because it's a 1, but if it had been like a 2 or something, then it would have come out as a 2 squared because it's inside the squared. But yeah, so these limits turn out to be 1, however you want to do that. And the limit at minus infinity is the same. By the same procedure exactly. This one's also 1, and so you get one asymptote for each number you get here. And since they're both 1, we just get exactly one of them. And horizontal ones are always y equals, because they're constant y values. So we get one horizontal. Now let's look at vertical. So the vertical asymptotes, remember, come from basically when you have division by 0. That means your function's either blowing up to plus infinity or minus infinity. And so here we look at when is the denominator 0. Unless, I mean, sometimes you have to worry about other things, like if it's a trig function, you might have to worry about other things, though you can usually reduce that to also being the denominator equal to 0. So here we would take this, square root both sides, and you get x equals minus 2. Okay. And slant asymptotes, there are none. Right, because the only way a slant asymptote can occur is if the degree of the numerator and the denominator are, or sorry, the degree of the numerator is exactly 1 larger, but here they're the same. They're both degree 2. So this can't happen. Okay, so we found these two asymptotes, and let's go put them on a graph. So let's get a graph going. Let's see. Okay, so we said y equals 1 and x equals minus 2. Whoops. Okay, so let's see, x equals minus 2 is maybe over here somewhere. Okay, and then we have a horizontal one at 1. Maybe I'll put 1 up a little bit over here. Okay, so this is y equals 1. And that came out kind of crooked, but I'm going to ignore that. Let's see. So those are the asymptotes. So when do we check for a slant asymptote? So you should always check for one, but the only time one will happen is like if you had, if this was x cubed plus 1 over like x squared plus 1, then the degree on the top is 1 more. It's cubed versus squared. That's when it'll happen. But if it was like x to the 4th, it wouldn't on top. Or if it was x squared on top, it wouldn't. So it has to be exactly 1 degree higher on top than the bottom. Otherwise, you can just say it has none. And then let's see, what was part 2? Local mins and maxes. So that basically means we should analyze the first derivative here. So I'm kind of just walking you through the steps we did the other day. So this is, let's do the stuff with the first derivative. So let me copy the first derivative for us. So the first derivative was this. And we're basically going to be interested in, where is this positive and where is this negative? And so the places it can switch are when it's 0 or when it doesn't exist. So the places where it's 0 come from when the numerator is 0. That's the only way it could happen. You work that out, you get -1/2. The only way that the derivative could fail to exist is if you had a division by 0. So that would be when the denominator is 0, at least in this case. There are other ways, like square roots and logs and stuff. So this would give us x equals -2. Okay, so we got 2 places it could potentially switch sign. Let's put those on a number line. And remember, it can be useful to keep in mind like which ones came from when the derivative didn't exist, because that usually indicates that can't be a local min or max, right? Because x equals 2 here was also one of our vertical asymptotes, right? So that means no matter what happens here, that can't be a local min or max, right? Because it's not even defined for the function. But otherwise, we do the same procedure as we've always done. We pick a point in each region. So to the right, 0 sounds good. In the middle, maybe -1. Maybe it's -3 on the end. We toss these into the derivative, because that's what we're checking the sign of. So here that would be 2 over 2 cubed. That sounds like a positive number to me. Sorry, and then in the middle, -1, that would be -4 over 1 cubed. And that would be -2. So that'll be a negative. If we plug in -3, what do we get? We get -12 plus 2 over -1 cubed. So now the top and bottom are both negative, which cancel out to be a positive. Okay, and what this question really asked was what are the local mins and maxes, and we see that -1 is a local min. Right. So then the way we would write our answer is that f has a local min. And because we're going to be putting this on the graph, it's useful to go and find the y value. So let's go and find the y value here. So f of -1/2. I'll save you the work and just tell you that it works out to be -1/3. Okay. And it has no local maxes. So it has a single local min at -1/2, -1/3. So let's go put that point on our graph so we don't forget. Okay, so -1/2 might be in here somewhere. -1/3 might be like, so we have a point somewhere over here roughly. Okay, and then we move on to the concavity and inflection point stuff. Feel free to stop me if you have a question.
So why do we not have a local max again?
So if we look at our diagram, you might be tempted to say -2 is a local max. But if you think about it, what we realized above is that -2 will be a vertical asymptote, right? So the function's either going to go like, it's either going to go like this or like this, right? So it can't be a local min because the function isn't going to have a value there. So the reason is, from our diagram, we saw that the only two places it could have happened are -1/2 and -2. And -1/2 was a local min, and -2 doesn't have a value, so that can't be either. It's neither.
Because we have an asymptote, right?
Right, correct.
When we answer these questions, do you want us to answer them with the coordinates, like both of the coordinates, or just f as a local min at -1/2?
So the way the question was phrased, I'd be okay with the way you said it. You don't have to put the y value. However, when you're graphing it, I will kind of hope that you do find the y value. So that's why I'm doing it, is because when you're graphing it, you're going to need that point anyways. So when you're graphing it, you do want to put the local mins and maxes and the inflection points, because those are kind of like the skeleton of the graph. Does that sort of answer your question? But if I don't ask you to graph it, then you would just be fine to say there's a local min at -1/2. And then the third one is, yeah, we're doing second derivative stuff now. And so let me copy. The second derivative was 2 minus 8x, x plus 2 to the fourth. Okay. And we repeat essentially exactly the same procedure, right? We ask ourselves, where could this switch signs? It could switch signs either when it crosses through the x-axis or when it doesn't exist, like, say, an asymptote. Okay. So the only way that this second derivative could be 0 would be if the numerator is 0. Let's see, what does that give us? X equals 2/8, which is 1/4. The only way it could fail to exist is if we had a division by 0. So we check when is the denominator 0, and that's when, again, at this vertical asymptote, right? We could have probably guessed that. Okay, so we found 2 points to put on our number line, 1/4 and -2. So -2 goes here. 1/4 is over here somewhere. And it might be important to remember that this one, -2 was a vertical asymptote, so that we don't mistake it for say a inflection point or anything. And then, yeah, we check a point in each region just like before, making sure now we plug it into the second derivative, because that's what we're checking the sign of. So we're plugging things into here. So 1 to the right here might be 1, 0 in the middle, and maybe -3 over here. And so, like, if we plug in 1, what do we get? We get -2 minus 8 over 3 cubed. That sounds like a negative number to me. We plug in 0, we get 2 over, sorry, this should be to the fourth. 2 over 2 to the fourth. Sounds like a positive number. -3 would be 2 minus -24. It's a positive number over, something to the fourth. If you want, it's -1. But it's positive over positive, so you again get a positive. Okay, so this tells us that, it'll be concave up where there's a plus here. It'll be concave down where there's a minus. And x equals 1/4, it will have an inflection point. Okay, and so the way we would write our answer here is that f is concave concave up, where there's a plus, so we just have to remove 2, minus 2. Right, because the divisions are really at these points, not at the dots. And then it goes up until the minus, which stops at a quarter. And it's concave down from a quarter onward. And it has a single inflection point of, so the x value is a quarter. If you wanted to find the y value, you plug it into the original, because that's what tells you the y value. I'll tell you that when you do that, you get some funny fraction. But you know, now that I'm letting you use calculators, you're free to use a calculator there. As long as it's, yeah. Okay, so you get an inflection point here. And you know, if you think about it, 15 over 81, this is smaller than a quarter. Right, because a quarter would be like 20 over 80. And so if we go up to the graph, let's see, what was the point? It was quarter, and then a little bit less than a quarter, but negative. So a quarter is over here somewhere. And so we'll probably have to erase this. And then minus a quarter is going to be up here somewhere. So it's going to be up a little bit. Okay. Okay. So that was all the pieces of information we've gathered together. Now let's try to put it all together. So in an ideal world, what you would have is you would try to look at these two diagrams together, right? And your graph all at the same time. But essentially what you do is you pick one region to look at a time. Okay, so the first region might be, let's see, like what happens to the right of a quarter. So let's look at this part. Everything to the right of a quarter. So in the first derivative, to the right of a quarter would be like over here. And that is saying that has a plus over it, so that would be increasing. In the second derivative, it would be here. So it's concave down and increasing. Okay, so we also know it has to approach the asymptote, so that means it has to do something like this. And then you kind of move on to the next region. So maybe you look at now the region between minus a half and a quarter, this region here. So then you go and look at the first derivative. Where does minus a half to a quarter come in? That's maybe this part. So again, that's increasing, which is good because it had to go up there. Here, it would be like in here somewhere. And so that's concave up. So concave up, increasing. You try to make it look a little nice. Get something like that. Right? So this was our inflection point. You can see it changes concavity there. It's probably not perfectly smooth, but... And then you continue on doing this. So like the next region would be what happens between our asymptote and minus a half. Down here, so that would be between minus 2 and minus a half. That would be here. It's concave down there. So, or sorry, not concave down, it's decreasing there. Then for the second derivative, that would be this part. And so it's concave up and decreasing. So concave up and decreasing really means it has to do something like this, because it has to, whoops, not that one. So, it has to approach this vertical asymptote by either going up to plus infinity or minus infinity. And so because it was decreasing, we knew it had to go this way. Okay. And then the final region would be what happens to the left over here. And you would see that it's increasing because of the plus. And you would see that it's concave up here. Okay, so concave up increasing. And we know it has to approach both these asymptotes. So really the only thing that's left is it has to do something like this. Okay, and that's a pretty decent sketch of our graph now. Then if I was being really accurate about it, I'd actually label what these points are. So this point is minus a half, comma minus a third. This one was what, a quarter, and then some funny fraction. And that would be it. Okay, so any questions about that? It does take some practice. No? Okay. So we probably only have time for like one more problem. Let's find a good one. Here's everybody's favorite type. Let's do one of these. Let's do a related rates problem. Okay, so take some time and give this one a try. Give you to maybe 3 o'clock, so 5 or 6 minutes. Give this a try, see where you can get, and then we'll talk it through. Alrighty. Let's go ahead and go through this one. So yeah, good old related rates. How should we start this one? So, it's worth spending the beginning of these problems just understanding what the situation is so that, typically for me that involves, drawing some sort of picture. And so what we have in this problem is we have a pile of gravel, which is in the shape of a cone. Should be a little bit more symmetrical than this, but and so what we know about it is that there's some gravel being dumped presumably on top of it, so that as it slides down, it continues to make the shape of a cone. And we know that there's a certain amount of gravel coming in per minute, 35 cubic feet. Okay. And then usually the next thing I would concentrate on is identifying, ultimately what are you trying to find? So in this problem, we're asked how fast is the height of the pile increasing, right? So how fast indicates we're looking at a rate of change. Like, so whenever we say like how quickly or how fast, that means we're looking at the rate of change of the height. Okay, so this means that we want to find the rate of change of the height at a certain value. So that means we probably want to give the height a variable name so that we can use it in equations. And so in our picture, h is the height of the gravel pile, right? From the ground up to its top, that distance is h. And so what we want to find is dh dt at the moment when the height is 15 feet. Okay, so ideally that's what we're going to come back to. Next thing I would say is try to understand what other rate of change information is given. So what we're given to work with is this 35. Okay, and so we have to think about like which 35 cubic feet per minute, like if you wait 1 minute, what quantity has changed? Like 35 has been added to what? So it's 35 cubic feet of gravel have been added. So we've really increased the volume of the pile by 35 cubic feet. So that means this is how quickly the volume is increasing. Right? So we probably want a variable name for the volume of the gravel pile. Okay, and so if V is the volume of the gravel pile, we're given that rate of change of the volume is 35. And it's a positive number because the volume is increasing. Okay, and so now we know, now we have two quantities where we're given information about one and we're trying to find information about another. And so usually what we do in math is we try to find some relationship between them. But here we don't immediately know a relationship between the rate of change of volume and the rate of change of height, but we do know a relationship between just V and H, or at least we know an equation that involves both those variables. So here that would be just the volume of the gravel pile at time t. So at any given time, the volume of the gravel pile is just the volume of the cone with that given height. Sorry, what am I writing here? 1/3 pi r squared h. Okay, but we have to be careful. Like, what does r mean here? We always have to be careful that we understand what the variables we use mean. So here, r is the radius of the base of our pile of gravel. Okay, and in these type of problems, it's important to remember like which of these variables are changing with time. Well, as time goes on, more and more gravel is added, and all these things are changing. I should just write. These all change with time. So if I take a derivative, they all should have derivatives that aren't just 1 or 0. Okay. So now we have a relationship between V, R, and H. But ideally, we would just want to have a relationship between V and H. So the idea is, sort of the easiest way to do it is we want to somehow get rid of R. And the way we do that is, in a lot of these problems, there's like an extra piece of information that helps you get rid of like the extra variable. So here, it says that the diameter and the height are always equal. Okay, so let's write the equation that says that mathematically. So that would say the diameter, which is just twice the radius, that has to be always the same as the height. That's not true in general. That's just true in this particular problem because of the way the gravel's working. And this lets us get a formula for R in terms of H. And we're going to take that and we're going to throw it in for R. Okay, so if we do that, squared H. So if I replace R with H over 2, I end up with this. If I simplify a little, you end up with pi over 12 H cubed. Okay, and so now this is a formula that involves a very direct relationship between the volume and the height. And so what we do is now to turn this into a relationship between the rates, which is what we're actually interested in. We differentiate both sides with respect to time. So we take the time derivative of both sides. And so the time derivative of the volume, well, the volume is changing, so it has some derivative. We'll just leave it as the time derivative of the volume. And then over here, we'll have pi over 12 sits there. Then you have 3h squared, just like normal. But because h is changing with respect to time, it has a derivative that's not just 1. So the chain rule, you get an extra derivative with respect to time. Okay, and so this is now our relationship between the two rates, which is why we call it related rates, right? Okay, so this formula here holds for all moments in time. What we do now is we focus on a single moment in time now. So at the moment, whoops, let's not use that. So at the moment when h is 15, right, that was what we were interested in. Now I can plug all my stuff in. So dv dt is always 35 for all moments in time. H at this moment is 15. And dh dt is what we're looking for. So that one we don't plug anything in for. It's what we ultimately want to solve for. So now we solve for dh dt. Okay, so if you do all of this together, let's see, you'll get 35 times 12 over 3 times pi times 15 squared, which we can cancel a little bit out, right? You can cancel a 3 out here. Uh, 13, we'll just leave it like this. Right, you could figure out what all these numbers are, but it might not be worth your time. So you get some number like this, but you should include units. So the units of h were just feet. The units of time were in minutes. Right, so the height is increasing. It's going up this amount of feet every minute. Well, at this particular moment in time, that's what's happening. Okay, and that would be our answer. All right, so any questions about that one? Okay, so mean value theorem. So let me just remind you of what it says. It says if you can check two conditions about a function, that it's continuous on a closed interval, say a to b, and it's differentiable on the same interval but open, or even on the whole thing, that's fine as well. That's also good. But all you need is the open part. So if it's differentiable on that interval, then if you know those two things, then there is a value c in this open interval. So between a and b is what we're saying. So that if you take the derivative at that point, it's equal to the average slope. The average slope is, remember, the average rate of change, which has this formula. So it's saying that the slope at a particular value is equal to the average slope. Or there's a point where the tangent line is parallel to the secant line. Okay. So in this problem, we need to verify, this function f satisfies these two things. So that's what we mean by satisfies, is we mean check the hypotheses. Okay, so if you just look at the formula x plus x over 9, and you ask where this is continuous, well, it's continuous on its domain. So that would be everything except for minus 9, where the denominator is 0. And that part, so remember the interval we're doing here is minus 6 to 0. So minus 6 to 0 is included in this, or minus 9 is not included in that, so this is still okay. That should be closed. If you take the derivative of this thing, I'll just tell you, you get 9 over x plus 9 squared, I believe. And if we want to understand where this is differentiable everywhere the derivative's defined, which is the same as where it was continuous. And that also includes the right interval. And here we only need the open part. Okay, so that was checking the hypothesis. We checked that it was differentiable on the open, continuous on the closed. And we found that by basically checking where was it continuous in general, and just making sure that our interval was included in that part. Okay, and then to figure out the actual value that would make that is guaranteed by the mean value theorem, we set up the equation that's given in the mean value theorem. So that would say we need to have f prime of c equals f of the end, which was 0, minus f of the beginning over end minus beginning. So if we work out what all those things are, this will be 9. And we don't know what c is. C is what we're looking for. F of 0 is 0. F of negative 6 is negative 6/3. On the bottom, we get a positive 6. So this works out to be a third. Okay, so we just do a little algebra now. So we have this equals this. Maybe we kind of cross multiply, we get 27. Right, I took the 3 to the left and I took the c plus 9 squared to the right. Square root both sides, so I get plus or minus square root of 27. And so this would say that c is equal to negative 9 plus or minus the square root of 27. And if you think about it for a bit, right, minus 9 is already less than minus 6. And so subtracting more off of it will be bad. So only one of these two is valid. The only one that's actually in our interval is the plus one. Okay, so this would be our value. So finding the value, you always just write down this equation and solve it for C. And you end with something. And sometimes you have to check that, all the answers you get are actually in your interval. Okay, so that's the last problem we're going to do today. I'll stick around a couple of minutes if there's questions, but otherwise I'll see you guys on, well, I guess I won't see you on Monday, but I'll be giving you your exam on Monday. And yeah, have a good day. Have a good weekend.